Sorry. Aha, thank you.
Thank
So
you.
you'd say that all again. I don't know. For some reason there was something strange about the way Zoom was configured today. Because it wasn't recording, and it came in muted, among other things. So sorry about that, Pedro. Uh, so here is an example of links between cells. Here's a compartmental cell where the nuclear compartment, the cytoplasmic compartment, and the membrane have been identified separately. Here's an example where we have an epithelium and we've identified basal, medial, and apical compartments. So we can't do as elaborate spatial structures as you could do, for example, the subcellular element model or true finite element model, but you can do pretty sophisticated cell architectures this way. And I haven't got as I say, I decided to change the order a little bit at the last minute, so things haven't been renumbered. And we may flip the order a little bit more. We'll start with the links, and then I have some review of the homework problems, and then was compartmental cells at the end. We can change the order if we feel like it. So here are links, and I should say that Giulio Belmonte is the one who wrote this lecture, and I don't usually give this lecture, so they're his slides, and I may need to check on some things too. So it's a good thing Pedro's online with us to help out. And so the basic idea of a link is that we are going to think about connecting either subcompartments of cells or potentially entire cells with elastic springs. And I say elastic springs, but they could in fact have other constitutive relations. In other words, an elastic spring, the force increases linearly with the stretch. But you could define a spring where the force was independent of the length, where it always pulled in. Philopodia tend to work like that. The tension force is more or less independent of the length. And if you wanted, you could do something strange where the tension was some other functional form. You're allowed to freely define the functional form of the tension. There's a very nice paper that's almost 20 years old now by Starus et al. And Deutsch. And that's a paper that we've never actually replicated fully. We had a student one summer in the CompuCell workshop who did it, but as far as I know, we don't have a demo of it or a publication of it, partly because there's bending modulus is a little complicated in CompuCell. This is a simulation that was done in the Morpheus modeling framework by Jörn et al. From Dresden in Germany. And this is a simulation of a single bacterium, a long rod-shaped bacterium. And they've modeled it as a string of beads. So here are a bunch of individual subcompartments of the bacterium, and then they put links between the subcompartments. And these links have an elastic component, but they also have a bending component. So there's a resistance to bending of the bacterium to make it rigid. And CompuCell has some capability to do that. I haven't played with it very much, so it would be interesting to play with that. But they were able to get various kinds of swarming of bacteria using that method. You'll notice, which we don't see that often in our simulations, we normally use a square lattice. You'll notice here in their simulation, they used a hexagonal lattice. And you can do that in CompuCell as well. This is an old simulation, which is quite pretty, which never got published. It's a pity, which was to model the formation of the eye cup in early development. In the eye, you start out with smooth epithelium, you get an invagination. That invagination pinches off and you get a separated cyst-like structure. And in here, if you look in detail, you see each cell is represented as a basal, apical, and medial compartment. And then you have apical constriction here in the red that pulls the cells together and causes the bending. And that's a simulation that we could try doing possibly either today or next week to see whether we could replicate that result. There's been work recently by Job, who's a graduate student who just finished his PhD in the Netherlands using CompuCell to simulate the formation of the spine, neural tube closure, and he used the same kind of method. Although his simulations are pretty complicated because they have a lot of molecular control in them, but the methods would work. So this is epibole in the zebrafish. This is early movement in the zebrafish. And you see, of course, in early development, you see these long, large-scale flows. And you also see, in this case, convergent extension, where you have cells coming in from side to side and elongating anterior to posterior. You also see a lot of cell differentiation and structural reorganization here, which we're not going to get to. But that kind of spatial reorganization is something that we can't model using just the techniques that we've developed so far. There are kinds of development that we have to have in addition to the kinds of force generation that we have to have in addition to the ones that we've had so far. In essence, all of the things we've done so far have been fluid-like movements, and now we need to have solid and directional movements as well. And this kind of movement is, I don't know if that one will play. This is a simpler version of what Abbas's eye cup formation was. Here we have an epithelium that's going to form a furrow here in the middle. This was simulation that was done by Giulio a long time ago of somatogenesis. It's called ectopic somatogenesis, where the cells polarize and reorganize in response to each other, and they form, in this case, somites. And here again, you have a apical constriction that's leading to that. And then here in the retinal neovasculature, you also have junctional adhesion, which then is lost, leading to failure of epithelial integrity. And so these are a bit more complicated simulations than the ones we'll do in class, but these are things that you can do fairly easily once you have a concept of solid links. And so the exercises are ones that Giulio has developed over the years. First, explaining how links work. Then we can go back to our old cell sorting simulation, do it with links. And then we'll, as usual, ask the question, how do we use links from Python? Because we'll probably have to control them independently. And we'll do cell crawling. It's possible, something that's missing in CompuCell, which was planned a long time ago and never got fully implemented, was the idea to basically have a center model where you could link CompuCell cells to the center model cells with a link. You can't do that, but you can create what are called anchors, which is you can create a link not to a floating point that gets moved around, but to a fixed point in space. So if you imagine a cell crawling on a substrate and sending out filopodia that anchor onto the substrate, or creating junctions onto the substrate, that you can do. And then I hope we'll get to it. There's the convergent extension model, which is trying to simulate that process that we just saw in the early embryo, where you have cells that contract in one direction and extend in the other. Something that is maybe not so obvious is if the cells, when cells go through convergent extension, they actually elongate they elongate in the direction that's shrinking, and the tissue extends in the direction opposite to that. So, sorry. So suppose that I had a square of written on rubber, and I drew circles on the square. And now I stretch the rubber like this. I'll now have ellipses instead of circles, but the ellipses will be elongated in the direction of the stretch. In convergent extension, the stretch is the same, but the cells elongate in the wrong direction. They elongate in the perpendicular direction. And that's a bit counterintuitive. And the reason they're doing that is because they're actually pulling on each other. And so they elongate in the direction of tension, which is the direction you shrink. And we'll see that in a few minutes. And that's a pretty counterintuitive result. If I had the cells drawn on rubber and I stretched it like this, there isn't any rearrangement of the cells. If two cells are neighbors before I stretch, they're still neighbors afterwards because I've just drawn the picture on the rubber. In convergent extension, when the cells elongate in the other direction, they have to rearrange a lot. So you have to make room for a lot of rearrangement as well. And that means in particular that the links can't be permanent the way they would in a solid. They have to form and reform in a plastic material, like a plastic material. So here's the basic idea. And the name of these is not maybe, like many names in CompuCell, they're called focal point plasticity, FPP links. And I don't actually know why there's the word focal point. Plasticity links make sense, or springs would make sense. I don't know why they're called FPP links. Pedro, maybe you know. But in any case, they anchor onto the center of mass of cells or cellular compartments. And that is, if you think about how the Potts algorithm works, that's really the only thing you can do. It would be more convenient if you could anchor them onto the membrane of the cell, but the membrane doesn't have an independent identity, so you can't do that. What you can do, if you're willing to pay a fairly heavy premium in terms of computational burden, is you can subdivide the region around the membrane into lots of little compartments, and then you can anchor to that. And we've had students who've done that in the summer, where they model one cell as a very large object with lots of little compartments around the edge. And then they define links around the edge to represent the membrane and the cortical actin. And then they draw links across the center of the cell to represent the actin links across the cell. And you can build fairly complicated biomechanics models that way. Really, if you're going to do that kind of model, you're probably better off with a more advanced center model like TissueForge or Mark Alber's method, or maybe HAL software from Moffitt Cancer Center, but you can certainly do it here. And so with the link, by default, the link behaves like a spring. And so you define the spring constant. We always use the letter lambda for the spring constant. And then the equilibrium length of the spring. Does it want to go to zero length? Does it want to go to some finite length? Minus here's the equilibrium length. So the actual length of the spring minus the target length squared. So in this case, if the length is shorter than the target length, the spring will push the cells apart. If the spring is longer than the target length, it'll pull the cells together. And again, you can in fact change the functional form here. This doesn't have to be squared. It could be linear. It could be to the fourth power or something else more complicated. But the basic idea is pretty simple. You have a spring with an equilibrium length. When we're going to use that, we go in our wizard, and there's a box that we haven't used. And in fact, when we've been running CompuCell Player, we keep seeing this message that FPP links are turned off. There's a little red message when you launch your simulation in Player that says, you're not using them, so I'm turning FPP links off. I don't know why it tells you specifically about that, when there are lots of other things that could be turned off too, but it does. So there'll be a box in Wizard called FPP plus the focal point plasticity, which we'll check. And we normally have center of mass turned on here, but you have to have that if you're going to use focal point plasticity. And neighbor tracker is also useful to have. Okay, so the FPP plugin in the XML, and as usual, we'll have both XML and Python versions of this. You specify links between pairs of cell types. So here we're saying between my cell and my cell, so that would be homotypic. But you could define a link that only occurs between basement membrane cells and epithelial cells. You could say that you only have links between pairs of cells of different types. And then you have lambda, which is the spring constant. Let's skip the next one for the moment. We have target distance, which is the equilibrium length. And then you have max distance. Max distance is that if the springs are stretched too far, they break. And having them break definitively at a particular length is maybe naive, but you can set up fancier rules, but that's the base rule. And then you have this activation energy and the max number of junctions. And these are a little bit less obvious, but the reason those exist there is that typically when you're going to do links, you're going to have to draw all of the links by hand. You're going to have to say, I want to create a link between this cell and this cell, this cell and this cell. And if you're going to do links, for example, in Physicell or in many packages, you have to do it by hand. We wanted it to be possible to not have to worry about that and be more biological. And so the concept here is that the cells automatically connect to their neighbors. And so if you have two cells of type 1 and type 2 that are next to each other, activation energy essentially gives you a probability of making a link connection between two cells that are allowed to have a connection. They can break if the distance gets to be above max distance. Number of junctions tells you how many links are allowed per cell. So typically in 2 dimensions, the average number of neighbors of a cell is 6. And so if I made the max number of junctions 10, then the cell will link to all of its neighbors all the time. But I might not want that. I might want the cells to only link to two neighbors or just one. And so you can change the maximum number of junctions. In practice, we tend to use Python and do these things by hand, but these are allowed for automatic creation of links. Yes.
So, so assume that I want one cell to have two linked neighbors, then I could say the neighbor order equals 4 and the activation energy equals 250%.
So the neighbor order here is calculated in terms of how you calculate how many neighboring cells you have. So, and I actually don't know that second neighbor order. Actually don't know what that second neighbor order specification does. Do you know, Pedro?
One is for forming, which is the one in max number of junctions.
Right. But I don't know what that second neighbor order calculation does.
Let me check in the manual.
I guess that means like moving one specific direction, allow you to have like two cells.
Well, usually the neighbor order is asking the question when you're determining if two things are next to each other. Sometimes if they touch just at the corner, you want them still to be next to each other. And so neighbor order of 1 means that something that touches at a corner is not actually considered touching. Whereas neighbor order of 2 means that things that are on corners touch. So this is really about artifacts of being on a lattice. I'm a little surprised. I probably wouldn't use neighbor order 1 for that. I probably would use 2 or 3, but.
Okay, so my question could probably like relate to not the neighbor order one, but the one for the max number of junctions. So like we are going to count the lengths between neighbors, combining the activation energy and the number of max number of junctions, or just the max number of junctions.
So the activation energy basically, again, this is a bit artificial. It'd be nice if the manuals, I think the manuals actually may go into more detail. The activation energy basically says if you are in touching another cell, it doesn't create the link instantaneously. There's a probability of creating the link. And why is that? The reason for that is, suppose that you have one maximum number of links is 1. And suppose when you go over your neighbors, you always go over in the same direction. Then the links will always point in the same direction. You want the links to form randomly. And so you want, as you iterate over the neighbors of the cell and say, do I form a link? 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 I don't want to always link to the very first one immediately. I want to be able to randomly link to one of the neighbors. I don't want to have a directional preference. And that's the reason there's this activation energy term. And we'll play with that in just a minute. We'll play with that. And you could change the activation energy. We could change neighbor order and see what they do. And so here, yes, there's this comment that the links break when the distance is too big.
James, apparently there is just one neighbor order. So the second one, the outer one, might be just a global value in case you don't set the neighbor order individually.
Okay, but I believe it.
In the manuals, it doesn't even show the outer one, just shows the inner neighbor order inside the specification of an individual link.
Okay, thank you. We'll have to try it. Maybe the syntax has changed. All right. So let's actually build a model of this kind. So if you can run CompuCell. And as usual, the menu order may be a little bit different from the one we have here. Because this is from a slightly older version of CompuCell. And Pedro, maybe you should try running it too, just so we can see if it.
Okay, I've already opened it.
Okay, so you've got a new project,
Yeah.
and so we can call this module links, something of that kind, usual. And then we're going to use the rectangular slab initializer. We can say 256 by 256. We do not want periodic boundary conditions for this. Okay.
Mhm.
And then we'll only create one kind of cell. You can give it any name you like. And no chemical field. And then we're going to select, we're always going to have a contact energy for our cells. We'll select focal point plasticity, volume. You need center of mass, and I would select cell neighbors as well there.
Mhm. Okay.
Okay, did that work?
Mhm.
Okay. All right. And let's run it and see what happens.
Mhm.
Boy, I noticed the formatting has gotten messed up on these slides. I don't know what happened to that. Looked okay last night on my other computer.
So I'm going to first enter the Zoom so I can share my screen.
Great, that would be great. And in player, you may have to click this FPP under visualization. You may have to click this FPP links so you can see the links.
Oh, okay.
It may not be enabled by default. You want to, there you go. Okay, so what happens when you run that?
Yep, like I didn't change any parameters.
Okay, that's fine. Okay. Can you make the cell field a little bigger so we can see? You can resize that, so it's okay. All right, so do you have the links in it visualized?
Yeah.
Okay. Sometimes it's useful to change the colors to make the links. If you can see them, that's fine. Sometimes the color choices, the default color choices make them a little hard to see. So if you go to CC3D preferences, under cells and colors, there's a link color and cell border color you can change if you want.
Sorry, where is the 630 problem?
It's at the beginning for you under CompuCell 3D
Oh, okay.
preferences.
Um, so here is like the.
So if you click on FPP link color, the bottom one,
Oh.
you make that dark, maybe something. I don't know, blue or. It would be nice if we could change the width of it, but I don't think we can do that. Okay. That's fine. Just any color you like is all.
Okay, balance, okay.
Okay, I tend to make it fine. Whatever, any color that you can see is okay. And then, did it stop? Did it die on you?
No, we still like so.
Huh. Oh yeah, okay, good. Okay, great. All right. So that looks okay. Why don't you open the XML? So let's look at the code that generated that. So you'll notice that each cell only has 2 links. So if we look at the boy, I don't know. I created medium links. That's a strange default because there aren't any medium links. So it's to cell is the only one that really matters here.
So we have like 2 parameter blocks here, like we have parameters and we also have internal parameters. And both of the blocks have cell links.
Okay, so this has changed a bit. So links are often used with compartmental cells. And so when you have a compartmental cell, the energy between the subcompartments within a single cell will be different from the energy between those same types of compartments in different cells. And so this is essentially creating code that would give you the template for doing compartmental cells.
So now we just need more.
So the only one of all of this long list of things, the only one that's actually doing anything is that one there, yeah.
So do you want to notify that?
So if you try, why don't you, to begin with, just change the maximum number of links to 6. And then try running it again, see what you got. And you can see here, you get basically 1 link per cell. So try 6.
Yeah, no, it's.
Now you see it's got, basically each cell is connected to all of its neighbors.
Yeah.
Okay, let's try one more thing, which is let's go back to the XML. And let's say what the equilibrium length of the cells, the links is long. So where do we define the link? The target distance. Here we've set the target distance to be 7, which is about the natural spacing between the cells for the size of the cells we defined, which was 50. But let's make the target distance between the cells 15. What do you think is going to happen when you do that?
Like it's going to push the cell away.
Right. So let's try that, see if it does that. So
especially at the boundary of the aggregate.
So let's see what happens. Well, it certainly pushed. It's done something sort of funny, which is it's pushing the cells away from each other, but they're still stuck to each other, so they're not actually separating.
There is probably because we also have like
Contact energy, yeah. So if you make the contact energy between the cells 0, then that might, sorry, you have to make it bigger because they're already. It's the contact energy is relative to the cell medium energy, so you make the cell contact energy bigger. Then
to 20.
yeah, that should do it. Let's see if that pushes them apart. Yeah, see now they get pushed apart. So that's actually behaving like a center finite element model pretty much, or except that it's an expensive way to do it because instead of having a point particle, you have a clump of points that are defining the particle. But if you wanted to build a solid mechanics model, you could do it based on this. It wouldn't be a very efficient way to do it, but you could do it. And in fact, I don't have any for this class, but I did a lot of simulations where you define a triangulation on a solid material, and then you define the material properties, and then you show the stress strain curves match what you would expect and that kind of thing. So you can define solid materials with different kinds of material properties this way. You always have a little bit of a problem because the lattice drag always pulls on the cells, but the links are off lattice. The links are between the center of mass of the cells wherever they are. They're not confined to being on the lattice. The problem with links really is just that there are two problems with links that I can think of. One is that they're slow, they're a little bit inefficient. The other one is they can wind up applying a lot of force to the cell. And if they apply too much force, they can tear the cell, they can break the cells. And so that can be an issue as well. Let's go the other way and make the target length of this links as 1 instead of 15. So now we'll be pulling the cells inward, compressing. So let's see, tissue gets
Slowly shrinking from
it won't compress all the way because you have the volume constraint that's fighting it.
Yeah.
And again, you can wind up tearing the cells so that their center of mass is moved relative to the, if you pull too hard. But you've already explored most of the things that we have to do. It's not such a complicated, it's not such a complicated idea. The thing that's the most inconvenient with links really is the fact that the link is not an object that you can address easily. So you have to remember you address a link by the cells on either end. When you're going to work in Python, you have to keep track of this is between cell number 16 and cell number 18. So you have to do some bookkeeping by hand when you do it in Python. When you're doing it with the XML, everything is taken care of for you, but you have a limited number of possible ways of controlling the system. So we've already done most of these little exercises. We changed the number of links, junctions. So here we had one, so some cells have no links, some cells have one, but no cell has two. And we've tried making that number bigger, seeing what happens. And in general, cells don't have more than 6 neighbors. They might have 7, but the average is 6. So this is an example of what it looks like with typically one link, 2 links, 3, 4, 5. And we also changed the target distance to make it more compressed and then extended it. And Julio suggested that we do this actually in the steering panel and player instead of in the XML, but it's we did those exercises. And we saw that if we make the target length very big, we can push the cells apart, especially if we have low adhesion between the cells. And if we make the cells stick together and make the lengths long, then we can get crossing. There's no exclusion that says that we can't have the links cross each other. They don't exclude volume. Now, how realistic those kind of tangles of links are, I don't know. Probably there are real biological situations in which you get something like that. So now let's do something a little bit more interesting. Let's create a simulation with 2 cell types. And now you're going to have 3 times the links, because you're going to have links between the cell. If you have, here he called it G and P for green and purple. You have links between green and green, green and purple, and purple and purple, and they can have different properties. And something we didn't play with in that first simulation was what happens when the links break. Actually, Pedro never tried making the target distance of the links longer than their maximum distance. Have you ever done that?
Yeah.
So they stretch and then they break and then they reform as shorter ones and stretch again?
Yes. Or they never break if you don't set a short maximum distance.
No, but what I'm saying is, suppose that I make the maximum distance smaller than the target distance. What happens?
Yeah, they pull each other apart and break, and then they have to come back together randomly.
I think that could be an interesting dynamic. We should try that. Anyway, we could try it here in this one. Because the 2 cells will get pushed apart, the link will break, and then it'll reform between 2 nearby cells, and then they'll get pushed apart again.
Yep.
So like adding the words.
But even for a single cell type, I think that it could be quite interesting. I'm sleepy today because I had my first Portuguese class this morning. At 7 o'clock this morning. For the next 3 months, I'm not going to get a lot of sleep because it's 7 to 9 every morning.
I have already added.
You got it? Okay, let's take a look.
Um, I'll just show you that somehow.
Okay, do you want to screen share it?
The noise is more smoother.
What did it complain about?
Um, um, I think it's probably because the XML format is not correct.
It's always a bit of an issue when you have
Exactly.
when the XML has a problem, then it often will crash uninformatively. So you have two cell types A and B.
And it's like, no, I can modify this XML manually, so it's just.
So the contact energy, if you replace it, it'll automatically update it for the number of cell types. So
Okay, can I just?
Yeah, the internal parameters you can delete. You're not using those.
And see the kind of cell types. Oh, yeah, cool. I think it's okay.
So in that case, you have the cells, the domains are
Oh, over.
overlapping. So what you want to do is just have a single domain and make cell type A comma cell B with one region. Yeah. And for some reason, you're not allowed to have a space. That's a parser problem. It should the parser should know how to ignore a space. Try that. There we go. There we go. That looks fine. So let's try something. Let's try before we try to change A versus and B separately. Let's just try that question that I was addressing a minute ago. So let's look at we can actually do it probably edited in the model editor under property. If we go over there, where we have focal point plasticity, FPP. If we open that one up, and medium we don't care about because there is no such thing. But so let's just do cell A, cell A 1.
Yeah.
So let's make the target distance 10 and see what happens. Should push them apart. That's fine. Let's let it run with 10 and see what it does. Okay.
Especially for this.
It takes a little while for it to go. Okay. And so now let's make the target distance 20.
Oh, you see the.
Okay, now they're getting pushed away. Now let's make the maximum distance 10. So make max distance 10. Okay, good. And now let's see what happens. So now what should happen is the cells that are far apart are not going to get connected because it only connects things that are near each other.
But you see like the right hand side, like
Yeah.
these two cells, you see like they're forming some incentive.
Right, when they touch, they should form a link. And then they're getting pushed apart from each other. I can't see the link because it's there. It must be one there.
It's just like instantaneous.
Right.
Instant.
And so what should happen is you should get something dynamic where the cells get pushed apart, the link breaks, and then it forms new links.
Yeah, but she has to set that to also cell A, cell B interaction. Because I think the links between cell A and cell B are resisting the repulsion.
Oh yeah, so you need to also change, open up the one that's under properties. No, same place. Go to properties. That was cell A. So let's do cell AB one too. Same thing.
This one, this one,
That's BB, so we could do the same thing. Make the target length 20 and the max distance 10. So you have to make the target distance 20.
Yeah.
So now we're pushing them apart radically.
Yeah.
But of course, if they don't touch or they're not close enough, they're not going to reform links. So,
You see, like,
all right.
some of the cells do actually touch each other, but
They still form links. Yeah.
and like quickly break apart.
Yeah. Yeah. Well, I'd have to look, I have to remember what the rule for it may, if there's no physically contacting cell, it may look for cells that are further away and then make a link. But you notice the blue ones are still staying connected because we didn't change the cell B connectivity.
If you want to check whether they have a contact, you could use step. And
Yeah.
you can see like there is a contact.
Yeah, right. Those are yeah, so when they touch each other, they're going to form a link. And then the link should push them apart. And when they get far enough apart, the link breaks and then disappears.
Yeah, with T cells,
Yeah.
both for the previous morpho
Yeah.
and this morpho cell,
Yeah.
they're not contacting, but
They still made a link.
yeah. So like that means you don't need to like have a contact.
Yeah.
But you still could form a link.
Yeah, I don't know what, as I say, I'm embarrassed to say that, but I actually don't know what the rule is when you don't have anybody contacting you. I'd have to look at the code to see the algorithm for determining how to link.
It's because it's within the distance. Like
That's possible. I never never is a long time. I rarely use the automated links. In other words, normally when I do links in the simulations I write, I create them in Python by hand, so I know which ones I'm creating. I don't use this automated creation and destruction. However, it's interesting to see how it works, and it's there, and it's pretty powerful. So I'm quite interested to see how this works. If we didn't have free space in the simulation, oh, so maybe the other way to do it would be, let's go back and make the cells adhere to each other. So if the cells stick to each other, so to make the cells stick to each other, you want to make the cell medium contact energy bigger than the cell contact energy. So if you flip it, instead of making cell A 20, you make cell A 10, but cell A medium, cell B medium 20. Now the cells are going to stick to each other. And now you could go back and you could make why don't we make the target length 20 and the breaking length 7? No, make it 10, make the breaking length 10.
oh, like the 24 typical cells, right?
Yeah. I mean, maybe 20 is too big for the target length, maybe 14, so it pushes a little bit, but not so much.
And this is for stuff I
The important thing is that the target distance is bigger than the max distance.
I think the cells are like the references to each other.
Right, so the red cells are getting pushed apart from each other. And, oh, that's sort of an interesting, that's actually rather an interesting, spot stripe pattern. That looks very much like the pattern you get in fish skin. It looks like a reaction diffusion pattern, even though it's not. Maybe it's worth making a note about that, because that's sort of an interesting exercise in its own, I think. And that's not a demo that I've seen. But that should be a pattern that never equilibrates, because as soon as the link gets towards its target, it breaks, and then you form a new link nearby. So that's a sort of an interesting.
Yeah.
How many it's 6? Did you use 6 for that? Okay. Let's make the number of links per cell into 2 and try running the same thing. So the max number of links is 2 instead of 6.
Yeah. But
No, you got 2 there. Okay, good.
yeah, I got 2, but
Yeah.
oh, here it's still 6, 8, 8. So um
I'm not sure what that one is doing, if it's.
it's a little bit different, but
Yeah.
not much different.
Yeah, I haven't, as I say, there are a lot of possible configurations here, and I haven't played with this kind of model.
Although like the cells
Yeah,
distribution pattern are not very different
Yeah.
from the previous one.
Yeah.
But you see like the links, like there are some local
right.
geometrical shapes
Yeah.
for the links. See it here. But yeah, so I think
So Pedro, I wonder if that global number of links, no, that was the interaction distance, so I don't know. But there is an exercise. Let me come back and let me just show you let me give you one other exercise, and then we can let you play a little bit more of this. So the goal here is, can you come up with a set of link rules that make the cells sort out, that make all of the purple cells come together, all the green cells come together, and the green and the purple separate?
you just set like the links between multiple cells and so like set the target or pretty short.
Well, and he makes the comment here that you should make the maximum distance small, like 7 or 8, so that the links break frequently. You don't want them to have. But if you want the green to come close to green and the purple to come close to purple, then should the link strength be large or small?
Is there like even the link string constraint?
Well, so we haven't played with the lambda link, right? We haven't played with that. So in this case, for contact energy, a bigger contact energy is less cohesive. But in this case, a bigger lambda, they're more cohesive. So if you make lambda green, green, and purple, purple bigger than green, purple, the greens should pull together and the purple should pull together and the green, purple should break more easily. Why don't you try that and see whether that works?
This one looks more sorted than the previous one.
Yeah.
Mm,
But I think here one problem is the links are too stable, so they're not breaking. Because if they don't break, then you're never going to be able to rearrange. So you have to make the breaking length small so that they rearrange easily. If you make the breaking length too small, then they never form in the first place. But but 7, I think is reasonable. So let's see. Yep, did it crash on us?
No, so, the target distance should be too small, right? Yes.
Yeah, I would say the target distance, the equilibrium is 7, so target distance of 7 is reasonable. Maybe 6, maybe 8, but you don't want the target distance to be too big. You don't want to be pulling on the cells too much. What you want to do is just nudge them to try to sort. And so, I mean, this is a bit different in the sense we've talked about cell sorting due to contact, due to differential adhesion. This is sorting due to differential attraction. That looks like it might.
There's the
Well, the blue ones get trapped, right? They get trapped in.
some of them, yeah. Normally the target one distance is a bit too small, so they would not like break the wall.
Well, that's definitely sorting. It's not sorting very fast, but it's sorting. So the one that he suggested was well, here he said max number of neighbors is for green. Green was 0. So then you'll never have any links between green and green.
Mm.
And then he said lambda green purple is 10. Target distance green purple is 1. That's very short. Maximum distance is 7. Max number of neighbors 3. Max number of neighbors So that'll only that, oh, this is a mixing one. This will make mix, this will be for mixing. So this will be exactly the opposite of what we're trying to do. And here's a sorting one. So he says high lambda for green, short target distance. 6 neighbors for green, okay. And then you're saying no, then he doesn't let you have any links between green and purple. And in this case, he's got green being a little more cohesive than purple. So.
And I'm pretty surprised that they set the target distance is pretty small. Like it's just one.
Right, that pulls pretty, that's quite a strong pull. That creates, if the target distance is much less than right, if the cells are going to be 7 by 7, then the typical distance between the centers is going to be 7. And so that means that the target distance is 1, that means that the force will be 36 because it's the distance squared. Current distance is 7, target is 1, 7 minus 1 is 6, squared is 36 times lambda. So that's a big force. I'm not sure I would have made it that different, but we can try what he came up
I
with.
think like after I changed I canceled the
Yeah.
max number of neighbors between
Yeah,
like a typical cell versus more sorted.
that's
It's a little more sorted. But I didn't change the target distance. Now the target distance is 6. It's quite small, 4
yep. So.
And there's no difference between the AA link and the BB link.
Yeah, that's pretty complete. That's pretty well sorted, the one you have there, yeah. And I'm sure if we played more, we could get it to sort more quickly or more completely. But it's interesting because this is a totally different mechanism for sorting from the one that we had. Now, for some reason, Randy has never gotten cell sorting to work in Physicell, but I would think this algorithm would work in Physicell too, because fundamentally, you're not the fact that the cells are extended objects isn't that important. You're basically coupling the centers of each cell to each other cell. So I think this algorithm should work in a center model as well as a Potts model. Okay, great. So those are some of the possibilities. There are actually quite a few possibilities, and one could play with that more and explore them. The other thing to do is to model actually philopodia. And in this case, you're really thinking about the link as something that's a physical object that's being thrown out and pulling on its neighborhood. In the first case, perhaps we think about the links as representing actin within the cell. Here we're thinking about a filopodial extension of the cell. And this is going to introduce the idea of controlling the cells from the links from Python. And normally we have to, and we're going to use Python instead of XML, we have to leave a blank plugin. In this case, we do it in a better way, which is we put in the local tag in the plugin. So if I remember right, and I think that that's the case. In this case, it's a little bit like the secretion plugin. We can do both the XML rules and the Python rules. So it's not like the volume where we either have to set the volume in Python or XML. In this case, we can do both, but we have to put that local tag in to enable the Python control. And his comment then is if you set the maximum number of junctions to 0, then there won't be any automated creation of links. You can still create them by hand, but they won't be created automatically. And then you can create links and update them and delete them and get information about them. And if you go to the Python code snippets under focal point plasticity, there are a whole bunch of options. Too many options maybe for links. And you'll notice that there are all of these different kinds of links. They're anchor associated. There are internal links. There are links between two cells. There are a number of anchors, there are a number of internal links, and so on. One of the main reason for this is that in general, the links don't behave like objects. They're basically things that are between objects, and so it's a little bit harder to reference them than cells. It's not bad, but you have to work a little harder to reference. So you can ask if we just look at all of these lists, you can say, look at all, if I have a cell, I could say, what are all the cells that are attached to me by a link? That's something I might want to do. Or what are all the links that connect to a particular cell? So you can iterate over a variety of neighborhoods. And then I can also modify for each cell, for each link, I can modify its maximum distance, its target distance, and so on. So I have the option of doing that. And there really are maybe too many options. I certainly haven't used all of them, but they're there. So if I look at the code here, to create a link, and it does have its own handle here, so it is an object from that point of view in CompuCell. Here, link equals self.new FPP link. That creates a link. And then I have to say which cell pair I am linking. First cell, second cell. And the term initiator and initiated isn't so clear, but this is the name, the handle to the first cell, the handle to the second cell. And then the lambda and the target distance and the max distance. And then I can also delete all of the links on a particular cell, self.remove all cell FPP links of cell, and that'll break all the links on that cell at the same time. That may not be what I want to do. I might want to change the rule, change it more gradually, but I can do that. Okay, so those are two of the functions that we have. And so here's the thing we're going to try to simulate. And this is a cell migration in an embryo. This must be lateral line, I think, where you have clusters of cells that move in a dense tissue. And they do that by creating links to the substrate and then moving forward and breaking links to the substrate. That's lamellipodial migration. They can also do that by sending out filopodia anchoring and pulling on themselves. So this is a movie of immune cells moving in a tissue. So that first one was more of a 2D movement. This is movement in a 3D tissue. And individual cells are able to move quite independently of the surrounding tissue, at least in some circumstances. Mesenchyme they can do. And so the model we're going to have here maybe is a little bit artificial. It's going to be based on filopodia. And so what we're going to do is we're going to have a single cell that's going to be different from the other cells. And it's going to have a direction of polarization, which is the red arrow. And then within that direction of polarization, it's going to look for cells that are near to it. And if it finds a cell, it's going to connect to that cell and pull on it. And if you see cells migrating or growth cones extending, for example, if you're looking at neuronal outgrowth or or vascular endothelial cell outgrowth, you really will see the tip of the cell will send out these long filopodial protrusions. If the protrusion touches something it can stick to, it anchors on that and then pulls, tries to shorten. It's a little bit like throwing a rope and you latch onto something and then you pull on the rope. Sometimes the filopodia don't find something they can anchor to, that they throw out and then they just pull back in. And so that's the game we're going to play. And I don't think, unfortunately, I don't know. Julia must have a Mac because the codec, this says that they can't play these media for some reason. I was going to try to recode them and the codec that he used to generate these movies doesn't work on my computer. So I can't play the movie. We'll have to, but if you saw the movie run, you'd see the cell throw out filopodia to its neighbors, pull, then destroy them, pull, create more of them. And so that's the algorithm, that's the game we're going to try to play. And of course, there's some artificiality here because we're going to predefine the direction the cell wants to move. In reality, that orientation would fluctuate. And so here's the algorithm for this. We're going to create, in this case, we'll make the cell, the domain a little bit long and narrow, and we'll make it periodic this time. And we'll add, have two kinds of cells, and he calls them red and crawler, although we could call them red and green or something else. You probably are too serious to watch anime. Pedro, you're almost certainly too serious to watch anime. But there was a somewhat comic action series last season called My Hero Academia Vigilantes, and the main character was called Crawler in that anime.
Balance for the China. The author. There's something related to the author, but yeah, I know that is very famous.
But in any case, there's a joke in Japanese because he uses the name in English, crawler, and the Japanese are always mispronouncing it. So that's a running joke in the anime, is that people call him something other than the crawler. His hero name is the crawler, but people always call him the something else. So that's probably not the most relevant thing to the simulation. I don't think that's why Julio picked the name here. And so in this case, we're going to have to do we're going to have to do the links by hand once we've got the things set up. So at the moment, this won't do anything because we haven't actually created the Python yet. And so we should see something like this. And we'll use uniform initializer to make all the cells initially red. Just create all the cells being red, and then we'll change the type. We'll change the type of the cells to one of the cells to be crawler type. And we'll also add the local tag to the focal point plasticity plugin, and we'll make the number of junctions, max number of junctions to 0. So I will make the contact energies too. If we make the contact energies too big, then the system gets sort of stiff. So we want the contact energies to be small enough it's easy to push cells out of the way. You should be able to share. I've got things set up, so you should be able to share. I've enabled both of us, so I could let me come.
So this is the initial condition.
Right.
And here is modify the contact region and cancel all the XML say for focal point.
Yeah, so the only links we're going to have in this simulation, well, I guess we could have the simulations between links between red and between crawler and red. We're not going to have any links between crawler and crawler because we're only going to have one of them. So let's just follow the guidelines here. So we'll use uniform initializer to fill the whole lattice with red cells. So at the moment, we're not going to have any yellow cells. So you should just get a lattice of all red cells. And there aren't going to be any internal links. Yeah. And medium, I don't know why it generates medium. We can get rid of that. It doesn't do anything. It blindly just generates every pair, but that doesn't make any sense. You actually can't have a link. I don't believe you can have a link to medium. You can, if you're going to want to link to a medium, you have to use the anchor links, which we haven't done yet.
So you would also get rid of these two.
Yeah, they're not doing anything.
So yeah, it's
And that seems to actually be a bug that was introduced into Player because it used to not generate all those extra types. And so we can make all the contact energies 2. And then in the FPP link section, okay. So now let's go into the uniform initializer and make it fill the whole space. So box min would be 0, 0. And box max would be whatever the size of the array you've picked. Okay, let's try that.
Oh, it's-
Okay, and then we only want we only want red cells to begin with.
do you like,
So so just red, no crawler.
okay,
Okay, so that's not so exciting, but that's from there, that's a good place to, if I get my cursor to behave myself. All right. Okay. All right. And now we should have that. Not very exciting. And so now let's go to the start function and find a cell that is that one cell, and we'll change the cell type to crawler.
use Python to do.
So you can iterate over all cells, check the center of mass of the cell. If the center of mass is in some range, we can change the type. So Pedro, if you're there, I have a question on what you're seeing. No, he's stepped away. I'm not used to switching back and forth between two screen shares, so I don't know if he's online, if he's seeing when I switch between the screen shares, I don't know if he sees it. All right. Does that work? I'm actually, I don't know. I don't know if you could, I didn't know if you could, I don't know if you can use range that way. I guess, yes, I guess there's no reason you can't.
Yeah, but probably like if it can't work, we just switch to.
Greater than and less than, yeah. I mean, it makes sense. I've never tried that. There are a lot of things you can do in Python that I never do because I'm used to doing them in a particular way. I'm often I'll write code and somebody will say, well, why didn't you do it this way? I say, because I didn't think of it. Or if I use something like Claude Code or Chat GPT or Gemini to generate code, it'll say, I didn't know Python had that command. Yeah, so cell dot type would just be self dot crawler, all capitalized. Whatever you called it, the yellow cell, if we call it crawler. Yeah. Okay, and then you have to do a break to get out of the loop.
Oh. Okay, probably will be choosing.
Just break, break, that'll do it. Yeah, that's just you want, fine, great. Doesn't have to be right in the middle, it's just have one. Okay, good. So now we're making some progress there. And now, oops, I have to find my cursor. Where's my cursor? The cursor behavior when I have multiple screen share going on is strange. Sorry about that. It's just, okay, so we've got that works. And now we're going to define these rules, which are going to be the angle the target distance and the maximum distance for our links. And in this case, he's suggesting we do a global. We don't have to actually global it, but it's useful. So at the very beginning of the code, we'll define a set of global parameters. And actually, if you're not going to change the values of those parameters, you don't have to call them globals. You can just define them without the global line. If you define them outside of the class, they're readable in the class, but you can't write to them, so you can't change them in the class. We could also use that shared steppable variables dictionary to do this too. But we'll follow the way he did it. It's a little bit different to see how to do it. He did it. It would be a little more interesting maybe if we had the direction, if the cell had a vector that was its polarity and that vector could change. But for the moment, we're going to predefine the vector just to be left to right instead of being relative to the cell polarity vector. Got that?
Yeah.
Okay. Okay, and now in the step function, we're going to every 50 Monte Carlo steps, we're going to delete all the links. So in the step function, after 5,000 Monte Carlo steps, why 5,000 Monte Carlo steps? He wants to equilibrate the mechanics before we start doing this. Every 50 Monte Carlo steps, we're going to delete links, and then we're going to recreate links.
Once these words are capitalized, I can barely recognize them.
Yeah, that's the fact that the type names are given by capitals is a little bit funny.
Finish the definition for deleting.
Yeah, so that doesn't do much. And then the create one is going to be a little bit more work because we're going to have to evaluate. So here we'd find the crawler cell. We find the neighbors of the crawler cell. And then we ask the question, is the distance between the cell and the neighbor close enough? And is the angle between the cell and the neighbor legitimate for the range that we're looking at? And if so, then we create the link. And it says from math and import A10 I think, yeah, I think that's. Yeah, so we get the angle and then we turn it into degrees. We could use radians, we don't have to do that. And the A10 I think here it says from math import star. I don't remember if that's a default. I think otherwise you could use, I think np dot A10 will work. NumPy.
I haven't used them before.
So
Probably.
I think if you look in your code, I think NumPy is loaded by default at the top of your simulation. So I think np.a102 will work. I don't think you have to do the math load. This is
But I also like the board the math, so it should be okay.
well, if you have math imported, then it's fine too, either way.
It's like
Right. Yeah.
it's a pie.
I mean, the only difference is that if you use the NumPy version, you have to have np.a102. Whereas if you import math, then you don't need to have a reference to the library. I can tell this isn't quite, I mean, I can tell this is Julio's code because the code is fine and it works very well, but it's not quite the way I would have written it. He has a slightly different style. It work?
Yeah, I just finished like doing so far. Let's see. Pretty sure. What is the one? Wait, I didn't see any.
You're sharing. Let's see what I.
Probably things like the
Okay,
volume.
okay, there you go. Got it. All right. The link's visible?
It's over like 5,000 more cost that. Then like it will.
Oh, the links don't start on yet, haven't turned on yet. Okay.
Two given.
Which is the line that has the problem? Probably the create link.
A two.
Oh yeah, A102 is different from A10.
No, it's just when I look back.
A10 by itself doesn't keep the quadrant of the angle. So what you want is the angle between two vectors. A10 just gives, A10 by itself gives you the arctan of one angle, not the difference between two angles. So A10, that's why you use A10. A10 too tells you the angle between two.
So back to it.
Yeah, so that's it's still okay. Yeah, sorry, I'm wrong. It shows it here. The problem A10, what is it? No, I don't know. I'd have to look it up. I don't remember. There is a diff.
Yeah. Two your phones too. It's arctan, arctan.
Right, it's arctangent, but the two, it's something to do, it has to do with the quadrant definitions, and I would have to check to remember what the what the rule is.
Yeah, that makes sense actually, because like y is this direction and x is this direction,
Right.
and we just wanted to calculate this.
Right, the smaller angle, yeah. Okay, so let's see if that works now. And we don't have to wait 5,000. We could make it a shorter waiting time. It doesn't take that long to wait. The idea was just to let the mechanics equilibrate. Okay, so now it says degree is not defined. Yeah, I usually just use things in radians, but he thinks it's
Now it's like, we just need to wait.
1,000 is fine. Yeah, that's plenty. It doesn't take that long to equilibrate.
Oh my gosh, I have so many typos here.
Well, he's made it. It's a little bit, it's a lot of typing normally. Let's see.
Oh yeah, it's the word, it needs to like, oh.
Yeah.
Probably.
I don't see the links though.
Oh, because the links is light blue colors.
Okay, I can't see them, but okay, so that works.
Yeah, it's pretty short.
Yeah. All right. And that's actually not a bad model of how a cell really crawls. At least certain kinds of cells actually do crawl that way pretty much. So it's pretty reasonable. And yeah, I can't play it, but that's, you saw what it's supposed to do. All right. So the next one would be, in this case, we're connecting the cell to neighboring cells, right? We find a neighbor, we connect to the neighbor. We can also connect to a fixed point in space, not necessarily to the center of mass of a cell. Now, again, it would be nice if we actually had a floating object that we could connect to, but we can only connect to a fixed object. And in this case, we're going to be able to, we can define sorry about the format here. Yes. Sorry about that. Let me fix that slide so that sorry about that. All right, so there we go. So again, but so far we've had links between a pair of cells, but we can define a link between a cell and an anchor where the anchor is some fixed position in space. So we give the coordinates of the anchor x comma y comma z, and then we treat it as if that were the center of a cell. So we can make a spring to a specific point in space. And so this would be an example of, for example, suppose that the cell we're sending out a filopodium, and instead of attaching to another cell, it's attached to the substrate. So that's what we're thinking. So the anchor link has exactly the same structure, except instead of having cell 1 comma cell 2, it's going to be cell 1 comma the position of the second point. Okay. And again, this is the kind of thing we're thinking about, the cell crawling. And we're going to use the same angle rules as we had before. And we have the same focal point plasticity as before. Oops, what happened? Did I lose? I lost some slides. Okay, so let's try this. We're gonna have to do this by hand because I don't have the I don't have the slide. So let's if you share your screen.
I think the only modification that we need to do is here.
You'll have to find the target position. And that may be a little bit tricky in the sense that we have to decide where we want to anchor to.
Yeah,
The easiest thing to do, it would be it won't look very different. But here's what we could do. We find the neighboring cell, we find its center of mass position, and we anchor to the center of mass position. In that case, the simulation should work exactly the same way it did before, but we're actually using the anchor links instead of the regular links. So if you screen share, we can see how that works.
I'm screwed. I am screen sharing and word.
So I don't see your screen.
Okay, so there's something right here.
What happened? All right. Don't know why. Oh, I know what it is. Okay, so my mistake. Okay, now I got it.
So I define the tree positions. So it's not a complete but I see one.
Yeah. Well, I see I'm ZOCC. No. I mean, Z we don't really need because we know Z is 0, but it's okay.
And so this method should be replaced with the method to get the distance between like two spots instead of
Right.
cells.
So now what we need is the only thing we really have to change is in that link equals self new FPP link. Let's go put your cursor below where we create the link in line 72, I guess.
Okay.
Okay, now let's go to the code snippets. And there should be a create FPP link with anchor. So it should be create,
Mm-hmm.
so create anchor. Let's see what does create anchor do? So,
Oh, you just have to be coordinates.
yeah, that's right.
Okay, so. Okay, so I'll just pass the.
So all that happens is line 71 gets replaced with that command there.
This is the. But this should also be,
Yeah, I don't think anything else has to change, does it?
oh, technically we don't have to change that because the focal point.
Is that the same place that we had before?
So it doesn't like have anything to do with the angle here.
Well, the angle is no, because the if still depends on the angle. The if in line 70 still
yeah,
depends on the angle.
The way that you calculate the distance,
Right.
the vector doesn't
Right.
bother
Yeah.
the angle, so.
Yeah.
They could do that.
Well, so we yeah, I think that should work. Let's try it. I mean, I don't know. It's possible that it won't break the link. I don't remember if we have to break the anchor links separately from regular links. Okay. Lambda distance. Okay, so where was that?
This one. Oh, is it? Why? Oh, they're all like not capitalized. So I have to pass the variable lambda. Okay.
Yeah, basically we need what we had before, but
Oh yeah.
except that instead of oh, but so Y cell is going to be now you've got to replace
I replace the neighbor with the coordinates.
yeah, so I'm actually confused about the one you used because it has X cell and Y cell.
Oh, this is the like the coordinates of the neighbor.
Right, but well, what is Y equals X cell, Y cell are the coordinates. Okay, fine. I get it. Okay, fine. That's fine. Yeah, that's fine. Okay, that should work. Well, should is the question. Let's see.
Oh. Let's see.
Did it crash?
Yeah. Just crashed and it says just closing local socket. So I was assuming it was also like a problem from the XML.
Yeah, but we didn't change the XML. So let's see, why would it do that? Let's put a try around line 76. 75. I know, I think that's right, yeah. We could,
Just print. Just printing.
okay. Because that'll tell us at least if that's the line that's causing the problem or not. I think it's most likely to be, but Because it got to 1,000 and then died, right? No, it still crashed. Huh. Okay, but let's see let's see what did it give us an error?
I think it didn't give me error. Because I have like a print comment here, so just print all of the ID. I'll just comment. And so
I wonder if it's not that, okay.
so if there is an error on that line, you're supposed to see the
Print error, yeah.
yeah. And here, so it's not.
So it doesn't print. Huh. Boy. Let's see, what is the problem here? Labor. Oh, we didn't define Z, did we? No? Yeah, no, I was just wondering if it was dying. I think, where is it dying?
Or if you want that slide by the way, just like add
Okay, yeah,
a lot of grades.
yeah.
Um, mm, yeah.
Okay, let's see what happens.
It runs like around 1100
Yeah.
molecules left. And then it just I think like I think the problem with
So it never gets to those print statements, huh? Oh,
no,
no,
you can see like there is
yeah.
so
So it does do it a few times and then it dies.
then I think it's the way that we set the
So it does do that print. So it looks like it's failing. It's got to be failing in the link creation, huh? But why would the link?
As the cell cross or a little bit.
Yeah.
And then like every like neighbor's angle is, like the focal point is larger than the 50 degrees.
So, but then it should just not create but then it should just exit the function without creating a link, right? If 71 fails.
Or we could just stop in front of like 1000 markers and step to
That would be good, yeah. I'm not sure how much time we should spend on this, but I just puzzled why. It looks like it should work. Okay, there you go. You can step it.
So now it's like 900.
Okay,
Just see a link.
I don't see any links.
Yeah, I see. Okay.
So maybe it picked the wrong.
For example, this must have like a link.
It should, yeah, but I don't see it.
Oh, and then like it just crashed. So,
So it seems to be crashing. So it seems to crash when it tries to create that link. And I don't know why. Target distance, max distance. Hmm.
XYZ, like voice sleeping.
Yeah, why don't you try the syntax of the next line? So
Now it works, but there's still like no links.
yeah, it doesn't look like it's creating anything.
No.
Well, let's see. I'm trying to remember what I had for the next.
Did you instantiate the links in the XML without specifying the parameters?
Well, she set local. You set the local flag in the XML, right?
Yeah, and yeah, here, and that worked for the previous simulation, but
Yeah, so it was working when we connected center of mass to center of mass. It's failing with the anchor.
Mm-hmm.
I'm trying to find the rest of error.
Oh, is there a separate? Let's see. When we created the links in the XML, is there a separate command for anchor? Oh, I know what it is. We didn't define the anchor. So go back to the XML. Go back to the XML. And now let's replace. Let's use the XML editor there for plugins and then do anchors, focal point plasticity. Let's just do focal point plasticity and do comment out. No, don't do replace. Do comment out and add. Okay, did it do it? So let's see what the options are here. We have type medium, 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 red. Scroll down. Let's see. We'll see all the ones we've got. So just scroll through these.
yeah,
Medium. Let's scroll down to the
this is the possible.
Is that it? Because can you scroll down?
Yeah, that's the XML file.
I'm not seeing.
Oh, this probably there's a delay. If you wanted to check the screen in my laptop.
Oh. Okay, internal. So what we don't have is the parameters for cell for I don't, it's not giving us a parameter set for the anchor, Pedro. Right? It's red to red, but there isn't a red anchor. Or is that used, do you use medium for that? Is that where you use cell medium?
Mm,
Or I don't know how you define the parameters for the cell medium one, or cell anchor one.
We could try to add, like,
So the syntax would look a little different, and I don't remember here. Let me see in my Twitter.
I'll check in the manual.
I don't want to spend too much time on this because there are other things we should do, but I just want it's just, since I don't usually use the anchors, I'm not. Because he carefully, I don't have the slide for the, I don't have the slide for the.
Can you show me your steppables?
okay, this is second. Here,
Okay, so for anchor in the demo, the online, the demo in the demos folder, there is no special one for anchors. Hmm. And the syntax looks right here.
we try to like add the medium signs, medium plugin signs, and we're like, we're gonna show you links here. After like 1,000 past that.
So the demo in the material, in the CompuCell demos, it doesn't look, let's look at the syntax that you have here.
Try just removing the conditional. Just let it create the anchor. Because the conditional might be
Yes.
messing up. Just to make sure it is creating. Because the command for creating seems fine.
Because if I look at the command if I look at the example which does work in the demos folder, it says anchor ID equals self.focalpoint plasticity plugin dot create anchor, parenthesis cell, comma, lambda, comma, target length, comma, max length, comma, X, comma, Y, comma, Z. That's it.
The conditional on 71 I meant.
Yep. No, but I was just trying to see what the,
Yeah.
what it looked like. Let's look at the call, because I wonder if the call here is, no, where you create the link. New FPP anchor, cell lambda target, max distance, PT. So they don't put it in, yeah, but PT equals point should be all right. But they just put X comma Y comma Z, but that's what you had before. That's what you had in the previous line.
Try removing the conditional 71, line 71.
I don't understand why the try isn't working. Because if it's crashing on the call, I would think the try would trap it, so it shouldn't crash. It didn't crash, but it's not doing anything.
Yeah,
So the links aren't getting, and you've got the links turned on, the visualization turned on.
yeah, it's on.
Mhm, yeah, okay. So it's not creating any links. Is it printing error in the console?
This is. I don't see arrow
No, so it's
and wait. Oh, it's reporting error.
yeah, so the try is failing.
Yeah,
So that for some reason that call is not accepted.
do you want to have a look?
Lambda, wait a sec. So we're passing, let's say, where do we define lambda?
Numbers at the top.
Okay, so those are global. Okay, global max target, max distance, target distance. Let's go back down. To your to your call, where you create the line. Where's your link?
Yeah.
Oh, it's still not, okay, we gotta wait. Okay, sorry. Target distance, max distance. Hmm.
This try to see if it reports an error.
So the call looks a little bit different in the demo. So let me see. This is the call in the demo.
Oh, the try here failed because it says the point 3D is not defined.
Oh, so then in that case, just use X comma Y comma Z. Don't make it into a point. So just get rid of there. Get rid of that and get rid of the extra parenthesis in there. Try that.
Okay.
Now I thought that's what we had before, but
It's you don't like quite the argument here, but yeah, when it crashed. Yeah, it crashed if you don't assign if you don't use the points.
X so Y so.
Are you setting these parameters?
Yeah,
Yeah, they're global.
Because it works here on mine. Like the anchor point. It's definitely not a problem of the function that works here.
Is there a typo in the name? But we used this before with where we did it between two cells, right? And it worked. Because we just copied, it worked before in line 72 worked. So why is it not? It's got to be something, quote, obvious, close quote, huh?
This is the only one.
Oh, I bet I know what it is. Huh. So put a float around X cell, Y cell, and 0.
No,
Float.
this is floating, sorry.
Just type the word FLOAT parenthesis.
Oh, okay.
Normally, 0.0, let's try that. Because normally, and if we can't get this, I think we should move on, because it's I don't like to give up, but no. So the only thing I can suggest here is if you go into go into Twit and go open a new simulation. So open CC3D project.
Mhm.
And now go to demos, go to CompuCell demos. There, go to CompuCell 3D, and then you'll find demos there somewhere hiding.
Yeah,
Okay, so under demos, go to plugin demos. And then there should be one called Anchor. Let's see. It'll be FPP Anchor. So scroll down. There are a lot of them. Focal point plasticity Anchor. There you go, that one. Yeah. Let's run that. See if that one works. It doesn't do anything interesting, but it does actually create an anchor point. So if that crashes, then the problem is a CompuCell problem. Otherwise, it's a syntax problem. So if that runs,
yeah, that one definitely works.
okay, I'm not seeing the screen update, but now, okay, there we go. Okay. So that has the syntax in it, which works. So I'm not exactly sure why, I'm not exactly sure what we did wrong, but that does show how to do the anchor creation. So we'd have to maybe cut and paste the anchor creator from there.
Yeah, I think I didn't see they use like new what is the function? New FPP anchor. You see, like in the script, they didn't use the new FPP method.
Okay. So it used a different creator, huh?
Yeah,
So maybe it's possible there's a typo in the code generator that
it's okay, I think.
well, I mean, I'm willing to try to debug it more, but I don't think we're going to gain a lot from if I wouldn't have done this, I wouldn't have tried this demo if I thought we were going to get stuck on that one. It's not a so I don't know what we should do. We're already at 2.5 hours. The one that's sort of a nice one, which is the convergent extension. Let's walk through let's walk through the discussion, and then we can decide if we want to do that, because I want to leave time for you to ask questions about the homework. So maybe this will be a homework problem then. Debugging the anchor one will be a problem too, unfortunately. But the idea here is convergent extension, and what you see in these early embryos is that initially the tissue that's going to form the embryo is relatively symmetrical, more or less a circle disc, and then it has to elongate head to tail. And that elongation happens in fish, it happens in amphibians, it happens in mammals. The way it happens is a little bit different in different organisms. In some cases, it involves a lot of cell division, in other cases, less. But the key thing that you notice is that you get cells moving from the lateral sides inward towards the midline and extending along the anterior-posterior direction. And as I mentioned, the cells are elongated perpendicular to the direction of elongation. So the cells are extended along the medial-lateral direction, but the elongation happens along the anterior-posterior. And that's a bit, in a sense, initially it looks surprising, but the reason they're elongated is because they're pulling. They're actually at the end of each cell, there are filopodia that are pulling on the neighbors, and that's what's stretching the cell. And that is a pretty universal thing to do. Now, if we really wanted to get the cell shape right, we would have to use compartmental cells where there were the two end points of the cell that could extend the filopodia, because at the moment, the pulling is going to happen from the center of the cell. And in that case, the cell shape isn't going to change. And so what you do in this simulation is very close to the one we just did, not with the anchor point, but the previous one, where we create a group of cells like this. We have to have some empty space on the outside, or this won't be able to reorganize. And then every so amount of time, now here he deletes all the links simultaneously, it creates all the links simultaneously. In reality, the links would be deleted and created more or less randomly. And then the rule for the link creation is exactly what we had before for the migrating cell, except that we could create both to the left or to the right. So instead of just having the angle be towards the right, we could also have minus that angle is also allowed. So if angle is less than, so you allow the angle to be on the other side too. And then so instead of having the cell, before we had the cell just create links towards the right. Now the cell is going to create links to the right and to the left. And all the cells are going to do that at the same time. And what you'll see happen is well, let's see if it's going to show us. No. I don't know why it's let me see if we have it at the beginning. Something like that.
So like all the cells which turn into like a thin layer of tissue.
Yeah, so I thought I had that. Sorry about that. I don't have a movie of it. Sorry about that. I don't have a movie of this. All right, let me put it this way. I do have a movie of it, but it's not in this slide deck. If you start with a round aggregate like this, what you'll see is that it will stretch in the vertical direction and come in the horizontal direction. And essentially, again, each cell is going to send out pull connections to its neighbors to the left and to the right. It's going to pull on them. It's going to pull on them for some amount of time, then it'll let them go. And then you do it again. And that is that actually is it works pretty well. And I'm sorry I don't have Pedro, do you think you could look for the convergent extension movie while I'm doing other things? Because I don't want to take too much time to.
On YouTube?
No, it's in our lectures. We have the videos. When I cut and pasted things, I somehow forgot. I didn't bring over the. Basically, I left a slide or two out at the end, which show the convergent extension.
Yeah, color impression, like a very abstract impression, but
Yeah.
if you like find it afterwards, you could just email them.
It's pretty, I mean, ironically, it's a video I show pretty often, but not when I'm teaching how to program CompuCell. If I'm going to show what CompuCell can do, it's a nice video where you see the cells move inward this way and stretch the other way. And as I say, it's in a sense, it's nicer if you use a compartmental cell where the filopodia don't come from the center of the cell, but come from the ends of the cell. And that looks more like the real experiment. And then the cells really do stretch, which you want. But the convergent is quite nice. So this works in 2D or 3D. And so that was a simulation that Julia wrote many years ago, working with Jim Sharp in Barcelona. And then for various reasons, Jim was doing the experiments and something happened and the student left. And so the paper never got published. So the method was developed and then it never got. In fact, that's not true. In the end, Giulio did publish. Pedro, there is a paper. If you search Giulio Belmonte, there is a paper which it's just called convergent extension, which has it. All right. So why don't we then spend the last 20 minutes that we've got? You had some questions about the homework, right?
Oh, yeah.
So let's come back to that and we can see what we can do about that. You said the delta notch. The one thing maybe I was going to talk about a little bit before that, and I'll just show you that. Boy, that got messed up formatting too. So have you tried steering panels?
Yeah.
Okay. So did those work for you?
Yeah.
Right. So let me give you the screen share and we can go back to your thing.
So, share my screen. Yes,
Okay, wait, this,
so this is the slider to adjust parameter A and B. For the two like parameters, it will be.
oh, hold on, before we do that. Let's see if this works. Maybe. Huh. No. Come on. Hmm.
I have a
Well-
slide with a few movies.
Okay, because I actually went to the original paper, and when I try to play the movies out of the paper, it doesn't work. So Pedro, go ahead.
Do you want me to screen share?
Yeah, please.
Okay. Do you see this?
Yeah,
This is the first movie.
Right, so that's the biological one. Oh,
Oh yeah.
now we want to see the simulation of the convergent extension. And for some reason, when I go to the PLOS-Comp bio paper, which we published it in, it doesn't actually want to play the movies. So this is still experimental.
Mm-hmm.
So do we have the simulation, the 3D simulation? There you go. This is the simulation.
Oh, what did it do?
That's it. That's what it should look like. Okay. So it's basically the same algorithm as for the cell crawling, but all the cells are doing the same thing, and it's putting out Filipodia both left and right instead of just to the right. Yeah. And in that case, he's added a little complication, which is he doesn't have all the cells extending Filipodia, only some subset of the cells extend Filipodia.
Yeah, for this one.
Yeah. But conceptually, it's pretty simple. All right. Thank you. So.
sure.
Yeah, so go ahead. You should be able to. Okay, what's that?
This is the slider,
Okay, yeah.
and these are both default values,
Yeah.
so just like that. The delta notch pattern always initialize from the boundary.
Yeah.
Aggregate, and it's always pretty symmetric with this parameters. But I remember like there's a question asking like if you increase the parameter A and increase the parameter B, like what is the difference that you observe?
Yeah, I mean, for some parameter values, you won't get a pattern. It'll stay neutral.
Oh, I did observe some, for example, if the B or A were too small,
Right.
there is no pattern, but and from the beginning, like even from the beginning, like they began to form this kind of pattern.
Right.
Like they're expanding, and then notice like very significant difference between, especially for those bigger values, for like both of the.
So one thing you can get, I'm trying to remember if it's true for this particular one or not, is there are two different kinds of pattern with delta and notch. You can get ones where you have high delta and high notch in the same cell and low delta and low notch in the same cell. Or you can get ones where you get high delta, low notch, low delta, high notch. And I think my recollection is, it's been a long time now since I've done that simulation. But my recollection was that there were particular parameter values where you could get basically delta and notch to vary together rather than in opposition to each other. But to be honest, the main point of the exercise was to do the sliders, not what happened to delta notch.
Yeah, but
I do remember that there are some parameters where you get some unusual, you get slightly different behavior from what you expect.
after a while, it would just recover again. Like if you,
Yeah, so patterns from the edge.
E and A like greater again,
Right.
and then you just recover.
Okay.
So yeah, I was just
And-
like, this is the only observation. that I-
Okay, well, that's fine. That's enough. Yeah. The other thing that, as I remember happening, but maybe doesn't happen for this particular algorithm, is that you can get situations in which delta notch oscillate. So instead of getting a stable pattern, a stable spatial pattern, you get oscillatory patterns. But it doesn't look like that's happening here. See, if you look at the notch one, there's a lot of intermediate values of notch, right? Delta is pretty much either high or low here.
Yeah, but there's still like a local transmission of speed.
Right, yeah, yeah. And definitely here, high delta, low notch. They're opposite to each other. The person we really need is Lorenzo, because he's expert in delta notch. He did a lot of experiments on delta notch. And I hope his paper is finally going to get published. We worked together maybe 7 years ago on a paper, which he submitted, and then he got some rather mean reviewers. And so finally, I think it's going to be published after 7 years of struggle. Well, it got a little bit complicated because he left the university. And so it wasn't so easy to he could keep working on the simulations, but he didn't have a lab to do more experiments.
It was like those wet lab experiments.
Oh yeah, he was doing,
Oh,
I mean, he really was doing delta notch experiments.
oh,
So he was working with endothelial cells, which do delta notch signaling. And so he put down a layer of endothelial cells in a dish and could watch them, and he could see them oscillate. So it wasn't that you got a static pattern. You got actually changes in delta notch expression in the dish that he could replicate.
I mean, like a real case, probably model
Is a little more complicated. Yeah, there are more delays in the model.
yeah.
But no, he had a fairly elaborate, I mean, not an enormous model, but he had more stages of the development. The Michael Elovitz published a famous model of delta notch that is used a lot, and it has more stages because in our case we don't distinguish between, right? We just have activated delta and activated notch. We don't have notch on the membrane, notch in the cell, and there are a whole cascade of signals, and there are other signals as well. The point of this model was it does pattern, one, and two, it's the least possible typing. It's the shortest model that does what we need. But I didn't have any great. I wasn't expecting anything too dramatic, except that if you make the values too small, you don't get a pattern. So The exercise was really more just to learn how to do
Yes.
the steering panel. And the steering panels in CompuCell are not great. We should have more different, we should allow you to do more kinds of sliders and things like that. But yeah.
Slightly.
Well, if you look in if you're in, say, if you're using Jupyter Notebook,
Mhm.
then the standard library for those kind of user interactions is IPyWidgets, and it has lots of options. It has many, many different kinds of interaction boxes. Here, CompuCell only gives you the combo box and the slider. It doesn't give you any of the fancy. And you have a limit to you don't have a lot of flexibility how you label the boxes and things like that. IPyWidgets is a fancier package. Yeah. Okay, but that looks fine to me. What you've got there looks fine. Now you said you had an issue with the Tyson model. Well, let's see what you got, because that one was one where I had all those slides, and then I had blanked out all those slides. Right. So I would just use the first two. You don't need all of the equations. So you just need the first two, actually.
Oh,
The-
I model like all of them.
You did all of them?
Yeah, so like
That should be fine. The 5 equations should be fine, but actually you don't need the other 3. The first 2 by themselves are an oscillatory loop.
Oh, I'm scared. I'm sharing screen now, and let me just play it. It's really oh. So it's really puzzling that 2 variables have a linear pattern, like
So what happened here? So it's a little hard for me to read. Can you tell me what the 2 variables you're plotting are?
oh, I have 5 variables.
Okay, but I can't read it's a little small. If you just tell me it's a
The red one, the CDH1
right.
molecules,
Mhm.
and the green one is the CCP molecule.
Okay, so they definitely should not be just growing linearly like that. So let's look at the antimony.
All
Wow.
so these are equations.
Can you possibly make this text a little bit bigger? Control plus. Okay, good. So you have nothing going to cyclin at a rate K1 minus, okay, you have a decay of cyclin. And then you have CDH2 1. A times, what is A?
Oh, it's a parameter.
Just 0, 0. So then it's just K3, KP times 1 minus CDH2 on divided by, okay, minus K4. Okay, so let's see. Okay, and then where's M defined?
this one.
Little lowercase m, yeah, where is that? Okay, fine. Okay. So and do you have M, are you overwriting M in the code in the Python?
Yeah, because it should be overwritten.
Right, so where are you setting M?
Here.
Yep, that looks okay. Okay, that looks all right. And you're saying when you run this, it just gives you a linear increase in the
I don't like
in the
so-
values.
Because it definitely like shouldn't give you a linear pattern.
Okay, so let's look at those other three equations, the ones at the end. How are they? Let's go back to the antimony for a second. So what are they doing? CDC20T, it doesn't affect the other first two equations at all, does it?
Um, here we have a site for the non-person.
Right, no, but it doesn't change, it doesn't affect, the first two equations do not depend on the remaining three, do they?
Oh, yeah, they're independent.
So let's comment out the 13 through 17, since they're not doing anything at the moment.
Yeah, and actually, like the linear pattern variables for this one, so it's not, these two variables are not linear, but they're not oscillating.
Okay, so let's just look at those two so I can see the,
So, I'll just like leave all of it.
I just comment out the plots for those three.
Yes.
Crashed.
Like the versions of the so it's a little bit
Boy, can you make the line bigger? Because I really can't.
okay.
Just make the, when you create the plot, make the width,
Oh, okay.
uh,
Thanks.
but you'll notice that the, if, okay, so just where you create where you create in lines 80 and 81, make size 10 instead of 1. Line 80 and 81, make size 10 may be too big, but 10, let's try 10, so then it's easy to see.
And another thing, I think they're corresponding to each other, is that the cell didn't divide.
Okay, so this looks okay. Yeah, so this looks fine. So these, I think, are doing what you want. Now, where's the cell? So the cell's getting bigger and bigger and bigger.
Yeah, it's getting bigger, and the concentration of the this one cation one molecules is also greater than like 0.5,
Mm-hmm.
and the volume obviously is greater than
Right. So this is, let's just let this run. Look at the picture there. One is coming up. It's not quite what you want, but it looks okay. In the sense one comes up. The other one, I think, is going to go. So they may need to be scaled a little differently. But I think, all right. So this doesn't look crazy. So now what, did you have the cell divide or not?
In my code I said like, let's see, like, the cell tolerance increases and, of the, wait. Oh, like, if the cyclone being concentrated in smaller numbers. And the last, um, you mean like just the, just the instant that,
Right, so you're trying to see if it's decreasing or increasing. So
but the cycle B is always increasing. So probably there is not going to be a moment that,
so let's go back to your plot. So which color is which in the plot?
the green,
So
the red one.
right, and so you want it to divide, basically when they cross. So so you want if when they cross. So it's if the red one is going down and the green one is bigger than threshold, then you want it to divide. So cyclin B is less than self-division threshold. Okay. And last is greater than division threshold.
So even like one is greater than the, like coherent is smaller than the threshold. And the cyclone B is greater than the threshold, so two.
So I'm not sure what you're so you what are you doing in line 66?
Just get the value in the previous, so you could just get the like the exact moment that the amount of cyclone is crossing the threshold.
Right. That's okay, but I'm just trying to so where do you set last?
Yeah.
No, but where do you set the dictionary entry? Why are you using a get in the dictionary?
Get means just fetch the value corresponding to the key here.
Right, but why not just use cell.dict bracket get bracket key?
Yeah, that also works.
So what is the, because I don't understand what cyclin B, why, I don't understand what line 66 is doing.
Oh, this is just to retrieve the past value. And this is the current value.
Right. And so where do you store, when do you store the last value? Here, okay, so why not replace line 66 with just last equals cell.dict cyclin cell.dict last. There's no dot. No dot after dict. Okay, so I'm not, that shouldn't change anything, but I just, the syntax was strange to me to do that.
for cyclone B drops. Huh? But the cyclone B just never drops, right? Like in my model.
Well, because it's not gonna, it's. So let's see, so why is it not coming down again? Because it should oscillate. It should oscillate as M goes up. So I think there may be a typo in the in the ordinary differential equation definition. So it comes up a little bit, which is what happens there. It's not tracking. It's not tracking the.
Oh, the mitosis. And then just like simply.
Okay, there you go. So what did you change besides that one line?
I um I I swapped the operators here. Originally, it's smaller than here.
Yeah.
And smaller than here, and I just observed that the cyclone B's
Mhm.
just increasing, so there's no moment that the
Right.
cyclone B's,
Okay.
you know, like decreasing, so I just swap. And now like it, at the moment, at the specific moment, the cell might like have mitosis.
Okay.
Oh, and but now you see like the cyclone B still keeps increasing. It doesn't like change the trend, like the trend,
Right.
because the cell divide. So I think like the supposedly if the cell divides, that would have an impact on the trend of the cyclone B.
Right. So green is CDH1, right?
Green is cyclone B here.
Okay. Okay. So if CDH1 is low, then the decay rate of cyclin B is low. And in that case, cyclin B will just keep increasing to saturation. So cyclin B only comes down when CDH1 goes up.
Mhm.
So CDH1, the first one does what? The first one the decay of CDH1 gets bigger when cyclin B goes up. And so suppose M is fixed. If M is fixed, what happens? If M is a fixed value, then so what should happen here? CDH1, why is it negative? Let's see, 1 minus. If CDH1 goes to 1, the first term is 0. So the rate of production goes down as CDH1 goes up. So that's a self-limiting production. And then as cyclin B goes up, you have even more decay. So if there were no cyclin B, CDH1 would go to 1 and stop. If you have cyclin B present, then your equilibrium value of CDH1 will be less than it was before. And if M is equal to 1, then what is K, what is K4? K4 is 0.04. So these are all, it's a little hard to tell from all of these.
Point, yeah,
Yeah.
0.04.
So what should happen? So it's not going to oscillate. Basically, what should happen is this: when M is small, CDH1 grows. When M is bigger, then CDH1 decreases. And when CDH1 decreases, then cyclin B goes up. So now what? Okay, so now you've got it oscillating. What did you change?
I changed the to K2 plus because you said like when the calculator molecules is low and the cyclone B is getting higher.
Yeah.
So I just tried to enlarge the coefficient of.
So you made K4 bigger?
I just want to suppress the cyclone B.
Right. So how did you do that?
So I just enlarged
K2
the
prime
K2
prime?
plus one. Yes, because that
Okay.
would just increase the decay.
Yeah, that makes sense. Yeah, and so now it works, huh?
Yeah, like you can see like there's a solution.
Yeah.
Not very beautiful, but
Yeah, but that's pretty close. So the thing that's, yeah, and now you still have, now you have division still, right?
like as the cycle B
Yeah.
increases to 0.5,
Yeah.
I'll just like dividing it. That's pretty slow.
Yeah, but that actually looks pretty good in the sense that you've got what's different here is that you basically you're cutting things off a little early. In other words, if you why did it not divide?
It's divided, but
There we go. Yeah. Yeah. So I think that looks pretty good. What's happening here is if you look at that plot, you see CDH1 goes down, cyclin B comes up and crosses it. You're cutting off, you're doing the cell division just after that crossing, right? You're just doing it. You're basically doing the cell division right here. Right here. This comes down, this comes up, and then you divide there. And then you start over again. Whereas this one waits until this comes up and goes down again before it divides. And you were seeing it coming up and you were seeing this curve here earlier in the first version of it. So my guess is that probably one of the parameter values that we had in the original model wasn't quite right. And I don't know which of those parameters it was. Here.
These are very subtle numbers. And he increased by 0.02, and just like it has a big difference.
Yeah, I didn't give you the parameter values, did I?
Thank you, John.
Yeah, so that's so we'd have to go, did you look how did you find them? Did you?
All of those problems?
Yeah.
Oh, I was like, set these equations and, I randomly just picked some.
Oh, okay,
Numbers.
okay. Well, so it's pretty sensitive to. So in the original exercise, the the original idea was that you go back to the Tyson Novak paper, which I should have given you, and pull the parameters there. I thought I actually had somewhere my mistake. If I do this again, I'll fix it. The parameter values were given. This simulation was actually used the version of this oscillator that's in biomodels. So there's a published executable version of the Tyson Novak oscillator in the biomodels database. And that's why I didn't have that's why this didn't have the parameter values here, because originally we read them from the published paper. But if you're telling me if you're telling me you picked the values more or less arbitrarily, I wouldn't expect it to work. It's pretty sensitive. The fact that you got it to work just now is impressive then. But the key thing, and I didn't walk you through the exercise, is basically to analyze. You look at that, you have to look at the equation and say, what are the feedbacks? Which is what I was trying to do there, to say, what do you expect to happen when and as you say, once you saw that, you knew which parameter to change to make it work. So I think that one went pretty well. Did you try this one?
Mhm.
Not yet. This one is more complicated to specify, but this one I know works because I wrote all the code myself. And so this is, and we're probably out of time for today, but this one is based on a paper of Zartman, where they modeled the calcium signaling. And so in the cells in the Drosophila embryo, there is calcium-induced calcium release from the endoplasmic reticulum. And so when the cell gets a certain amount, it's a little bit like a neuronal firing. When the cell gets calcium from outside, if it goes above a threshold, then it releases internal calcium and releases even more. So the cell stores calcium in the endoplasmic reticulum. If the calcium level in the cell goes above a threshold, then the calcium in the endoplasmic reticulum is released. You get a spike of calcium, and then it starts pumping the calcium back into the endoplasmic reticulum. So then there's a fast increase of calcium and then a slow decrease again. And so that's what this model is about, is the pumping of. So here the first one is here is flow of calcium from the neighboring cells into the cell. And then there's a cytoplasmic calcium that's really too small to read. where basically you get the pumping of the calcium. IP3 is the ion channel that pumps the calcium. And then this is the calcium in the endoplasmic reticulum. So the calcium gets transferred from the cytosol to the endoplasmic reticulum, and then at some point it gets released back in. And what happened? And then there's a whole bunch of experimental parameters. Again, maybe it's not worth worrying about this one so much. The reason I didn't expect people to really focus on the individual oscillator, although you can get oscillations just with a single cell of the calcium. And then what you could do is you could look at what happens to those oscillators as you change critical parameters. There's a particular threshold parameter, this VPLC parameter, which as you change it, the period of the oscillator, it gets faster. The oscillation period gets faster. And then you can actually do a full bifurcation diagram of the oscillation. If VPLC is too small, you don't get any oscillations. Then there's an intermediate regime in which you get oscillations. If VPLC is too big, you don't get oscillations. And so that's something we did. And then what we do here is we start out with just one cell that's spontaneously oscillating. And it sends the calcium to the neighbors. Then if enough calcium gets into the neighbors, then they release the calcium, and that sends a signal to the neighbors after that, and then so on. And maybe again, it's not this one is, and you get traveling wave oscillations. In reality, there's also a little bit of mechanical contraction that happens when calcium is released. So you get a little bit of mechanical adjustment of the tissue as well. Maybe it's not that exciting to do that simulation. The thing that's in this case, in a sense, what's interesting is the result, which is that you see these traveling waves of calcium release in the tissue. So you see a single cell that pulses calcium, and then you see an excitatory wave of calcium going out from it. And that's seen in the experiment. So that's really the point of that exercise. The details of exactly how the calcium model works are not, they're interesting, and Jeremiah spent many years making experimental measurements to validate the details. But if you're not interested in Drosophila induced calcium release, it's not so exciting. The point was more to see how in the delta notch you get patterning, but you don't get oscillatory patterning. You get fixed patterning. Here you get oscillatory patterning. So the point of this was more to show how oscillatory patterns work. It's not that essential. I mean, if you're interested in the biology, there's quite a bit of interesting biology in how this signaling system works. But it's not essential. It's not essential to understand that. It was, again, more to illustrate how to do coupling between cells. And in the delta notch case, you have coupling between cells that leads to that stable or nearly stable delta notch counter pattern. Here, the coupling leads to a traveling wave of oscillation. So that was really all that was there. If you haven't done that problem and you've spent enough time on it, I'd work on the project more than that. we're already a bit over time. The only other thing I was going to say is, and we don't need to do this today, is the last thing the next time I want to talk about compartmental cells and how to do compartmental cells, because that allows you to build these complex architectures like tubes, stable tubes, cysts, polarized epithelia, and so on. And then that in turn allows you to build things like, spontaneous polarization in cells. And mostly that's based on the simple contact energies that we've done before. But now you have contact energy for compartments within the cell and contact energy for compartments between cells. So that's where all those flags for contact internal or link internal come from, is when you have compartments.
Do you have like internal flags for contact energy?
Yeah.
Oh, it just be sample code and show. Okay.
There's a separate, yeah.
Okay.
And so that's really what I wanted to talk about today. I think that's plenty. Was there anything else you wanted to talk about today? I'm sorry about not giving you the parameter values. They were, as I say, originally